So we also have another theorem for existence and uniqueness of solutions to differential equations. This one applies just to first order ODEs, but it doesn't have the requirement of being linear like we saw in the last section. So any first order ODE that can be solved for y prime can be written dy dx equals, and then over here on the right hand side we have some expression in terms of x and y, and so I'll just call it f for lack of anything better. So it's just some expression involving x and y. And we also have our initial condition. We pass to the point x equals a, y equals b. So such an initial value problem is guaranteed to have a solution and a unique solution on some open interval containing the point a whenever f and the partial of f with respect to y are both continuous functions at the point ab. So let's look at an example. For instance, if I took y prime equals y squared, then in this case our f of xy is y squared, and the partial of f with respect to y is 2y. And so since these guys are both continuous at at any point, then we know that there's going to be a unique solution. So for example, if I were to add an initial condition of, say, y of 0 is equal to 1, then there's going to be exactly one curve, one solution for that differential equation. It turns out, so that the point is, so the theorem tells us that since those guys are continuous, there's going to exist a unique solution. It turns out that the solution is 1 over 1 minus x, and this is valid on the interval from minus infinity to 1. And so if I just sketch what it looks like, it'll look something like this, right? However, we're looking at the one that passes through the initial condition, and the initial condition is this point here, 1, 2. And so only this curve here passes through that point. And so that is the one that we're looking at. Okay, how about another example? We'll take x times dy dx is equal to 4y. Okay, so now this one is not written in the exact form that I showed you above. So namely this one right, oops, pardon me, this one right here. So I have to solve it for y before we can go on. So let's go ahead and do that. So I will divide by x here, and I'll have dy dx equals 4y over x. So that's my f of xy for this example. And then my partial of this with respect to y. So let's see. So then I'm just going to be treating the 4 over x as a constant and differentiating the y, and the derivative of y is just 1. So my partial is 4 over x. And these guys are constant, or sorry, not constant, what am I saying? Continuous. For x not equal 0 and any value of y that you'd like whatsoever. So as long as I'm given some initial condition like, let's see, y of 1 is equal to 3 or y of -1 is equal to, I don't know, -12, whatever. Anything like that will be fine, and there will exist a unique solution. Oops. Through that point. If I'm given an initial condition like y of 0 is equal to 1, then what can I conclude from the theorem? Well, nothing. The theorem doesn't apply because it's not continuous at this point. So it's a big question mark. Cannot conclude either a yes or a no.